Good afternoon, and welcome back to the afternoon sessions of the Sustainable Food and Farm Conference. Reality check, how are you all doing? Are we learning stuff? Are we going to make a sustainable community? Yes. All right, I would like to introduce a friend of mine. He runs Vital Garden Supply. And Vital Garden Supply came around from Brian studying with Elaine Ingham. Remember we had Elaine Ingham here? Okay, so, Brian's good friends with her. Anyway, he has Vital Garden Supply. And his whole family is into his store, 3 generations, which is pretty cool. And I'm going to let Brian come up here and introduce our next kind of wacky speaker. All right? Come on up, Brian. Brian Mellon.
Thank you, Cathay.
Okay, let's get this out of you.
Good afternoon. Good afternoon, everyone. I'm Brian Malin from Vital Garden Supply. I would like to thank Sierra Harvest for putting on such a great event year in and year out. We are very fortunate to have the food and farm here in Nevada County. It's been really great to watch it grow over the years also. I especially want to thank Sierra Harvest for bringing such top-notch speakers year in and year out also. One of my favorite speakers over the years was definitely Elaine Ingham, the author and mentor for organic and biological practices. And then there was Paul Stamens. He was pretty amazing also. The king of fungi perfecti. And then Bill Mollison was really great to see as well. And this year we get to see Jeff Lowenthal speak and spread his knowledge. What I really love about Jeff is he breaks down how to benefit from combining organic nutrients and beneficial microbes. He also has some pretty funny jokes. So without further ado, I'm pleased to welcome Jeff Lowenthal to the 2019 Food and Farm Conference. Thank you, Jeff.
Thank you. Okay, I have to make, whoa, look at that. Just almost spent $3,000 on a new computer. I have to, no, I don't need that. Whoa, 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 whoa. Sorry, folks, for this. How am I sounding, all right? How am I looking? Not so good, not so good. Okay, hold on a second here. I don't know what this is, but you can.
This is sound. You don't need sound right
Okay, no, I'm good. I think I got sound in there. All right, let's see if we can do this. If Steve Jobs will let me. Now everybody knows my passcode. All right, so my name is Jeff Lowenfels. Thank you for being here today. I don't know what to tell you. I'm going to give 2 different kinds of talks. This one is a talk that's just sort of to relax you a little bit. Don't take any notes, nothing you're going to need to know, but hopefully you will enjoy it. At 2:45, I'm going to go into soil very deeply, but this is a talk on my second book called Horton Here's a Who. I gave it for the first time in the birthplace, I didn't realize it, of Dr. Seuss. And I was walking around in Connecticut, Hartford, Connecticut. I was walking around, there was Dr. Seuss statues everywhere in the hotel that I was staying at night. And then I got to the convention center, and there's statues all over there. I didn't realize he was from there, so I apologized to him. A lot of people don't know who I am, but a lot of people know who the guy with the white beard is. That's the guy from the Victory Garden. And he and I went to college together, along with a third guy, Bezo Cutler, who's here someplace. Bezo, where are you? There he is, right there. Roger and I both ended up being garden writers. I like to tell people that the class of 1971 of my college, 2% became garden writers, and 1% became successful at it. Anyway, I now have a trilogy of books. I used to have just 2 books, and I used to call myself, because they were on soil, America's Dirtiest Lawyer. But since I have a trilogy now, I call myself Lord of the Roots. All right, so the first 2 books really talk about, or the first and the third book, really talk about how the nutrients in the soil get to the plants. How they get to the plants. And that's pretty important because it has to do with soil structure and the soil food web, et cetera, et cetera. but it has nothing to do with how plants take up that food and what they do with it. And one day, of course, this is the soil food web, which I'll be talking about later on. You have the photosynthetic energy goes into the plant. The plant uses about 50% of it to produce things that drip out of the root system, and it attracts all the members of the soil food web, and I'm going to talk about that at length at 2:45. That's how the food gets to the roots. But, how does the plant eat? It's just one of these things I couldn't figure out. So the food gets to the plant. What happens next? And so you always see pictures like that one there, with things moving into roots, but they don't tell you how they move into roots, and I watch people eat. I know how we eat, but I couldn't figure out how plants eat. It was just bothering me, and I needed something to do, so I, started looking around, and you see all this stuff here we all know about, CEC, cation, things stick to the clay, and blah blah blah, and then of course you get pictures like this, which talk about, and they always end up with little arrows running into the roots. What does that show us? I couldn't figure it out, and then then we get more, we get this one. This was a classic. You see this all the time, something like this. What the heck is this? And of course, it's got a lot of these hydrogens there, and then you get to this one. This is sort of, diffusion and interception and mass flow. Again, and then an arrow going into the plant with a bunch of arrows going up the root. What does that mean? It's just one of these things. So, in one of my looser moments, I decided when my wife wasn't around that maybe I should figure this out and write a book about it. So I did. I wrote a book called Teeming with Nutrients. The wonderful name they gave it, The Organic Gardener's Guide to Optimizing Plant Nutrition. Is that sexy or what, huh? God. Anyway, this was really a case of curiosity killing the cat. Because it really was beyond my comprehension. Chemistry, botany, and cellular biology. I need to get all these things and learn all this stuff. Should have learned it in college, never did. So let's start with chemistry. Now, I would have been a doctor today if it had not been for chemistry. And I think I'm allowed to say this about chemistry because if you look at this chart, you'll see that the number of chemists that are graduating from colleges in the United States is going way down. So the chances of too many chemists being in here to beat me up, are pretty low and getting lower every time I give the talk. So I would have been a doctor had I not had Chemistry 1 and had all of this methyl ethyl chicken wire stuff up on the thing. I couldn't figure out what, and Bezo probably was in the same class, and we would have been doctors, and so I became a lawyer instead. This is what I think about chemistry, really. But when you get right down to it, what's chemistry about? I can tell you in one word. It's about bonds. Chemistry is all about bonds. How do things bond to other things is what chemistry is about. And it all is based upon, the atom, where you've got the nucleus, it's got the protons, and then you've got all of these electrons that are surrounding, when I was a kid, they were in orbits like this. And then a little later on when we went to space, the orbits became like that, like atoms. But in fact, they're just really basically sheets. They're a plasma that travels around, so you get this little M&M shell around the chocolate, and it's got, and this M&M shell at the outer one is supposed to have 8 electrons in it in pairs, okay? So that's the rule. It's called the law of bonds. And if it doesn't have 8 electrons in pairs, then it's active, and it can bond with something else by either borrowing or taking an electron from something else so that it can complete the pairs and have those 8 electrons. Pretty simple. It took me 6 months to figure this out, but that's it. 8 electrons, 8 protons, 8 neutrons, and everything's in balance. This is the oxygen molecule. It's got all of these things running around the outside of it, and these bonds enable atoms to connect to each other, okay? And you've got 2 basic kinds of bonds, covalent bonds, where the 2 atoms share equally. And then you have the ionic bonds, where one of the molecules gives the molecule to another molecule. They don't really share it in the same way. It's not an equal sharing, and those are ionic bonds. So there's only 2 kinds of bonds. And again, you spend 6 months in chemistry, and that's the only lesson that they're trying to teach you. So it's pretty simple. And when atoms bond to atoms, you get molecules. Okay, simple as that. And so let's talk about water. Water is one of these incredible things. We all know it's H2O, right? So it's 2 hydrogens and 1 oxygen bonding together, and they bond together because this group is able to make these pairs, these 8 pairs, work for each one of the molecules. And so it turns out that they don't share them equally. They share them unequally, and at the top and the bottom, they're polar. So they're polar covalent, and that's what it looks like. And they're very small molecules, and these bonds are very, very small. So just to get a feel for how small we're talking about, a hair strand's 100,000 nanometers, and a water molecule is less than a nanometer. Okay, so we've got this teeny size, which is very, very important. And so just again, to show you how what these sizes mean, if each of us on the Earth was 1 nanometer tall, we would all fit into this pansy thing, and there'd still be room in there because it's really, really small. So water molecules are incredibly teeny, unbelievably teeny, and they have these very special bonds called hydrogen bonds. And I'm not going to go into it too complicated, but the deal about hydrogen bonds in water is there are gazillions of them. And they're very weak, but there's so many of them that they hold the water together. And it's a very special kind of bond, which is magical. And so what happens is you get these water molecules attaching to each other. And so first they can attach 1 dimension, then they can attach in 2 dimensions, and then they attach in 3 dimensions. And as a result of that, you get surface tension, you get, this kind of stuff, and water holds itself together because of these wonderful hydrogen bonds. And it's a very regular molecule. So it looks like this, and what it's got the capability of doing is being either ice or water or vapor all at the same time. Now this is unusual. There's really very, very few other things that do this, and it's because of these special hydrogen bonds that they have. Now, why would you care as a farmer or a grower? We all see this kinds of stuff, but what happens a lot of times is you get this, on the leaf, right? So you get water on the leaf, and when you get water on the leaf, it makes it a little tough for the leaf. The surface of the leaf, the stomata area, it's very irregular, and all that water just sticks right in there and creates a barrier, a vapor barrier. And it prevents the stuff from inside the leaf going out, right? Oxygen and CO2 from going in. And it also traps water inside. So it's not a great thing, but it's because of these wonderful capabilities of this hydrogen bonds that you've got water that can be a gas and a liquid at the same time. Now, the other thing about water molecules is that they are the ultimate solvent. They can surround other molecules like nothing else can. And so as a result, water is a phenomenal dissolver or a solvent. Now basically that's all you need to know about chemistry as far as how plants eat, except for diffusion and osmosis, which we all learned about in high school. If you've got all sorts of concentrated molecules on the left-hand side of a barrier, and on the right-hand side of the barrier there aren't any of those molecules, then the molecules tend to move towards the empty space. They go through the barrier, and they try to equalize themselves. And so if it's a gas, it's diffusion, and if it's a water, it's osmosis. So that's all you really need to know about chemistry. And again, if I'd had a professor that sort of taught me this stuff early on, I would have been a doctor instead of a lawyer today. Now, the only elements that a plant needs are these, right? They don't need the entire 100 and whatever the heck things on the periodic table. They only need these 18 elements. Now, you take these elements and you think about it, you can't play a game of cards with that few. It's too few. It's just not capable. But if you take the math and do the combinations of those few elements, this is how many different combinations meaning different molecules you can get just with those few elements that a plant takes in. It's pretty incredible, frankly, and the math is billions and trillions and quadrillions. I can't even do it. And what makes these things work, in addition to these bonds, is the ability of the molecules to get close to each other. And they get close to each other as a result of enzymes, which we all, again, learned about in high school. I think when I was in high school, it was a lock and a key situation. They've got all sorts of different ways of explaining it now. But molecules are held together by, or put together by enzymatic activity. And so in a single cell in a plant, there are 42 million enzymes in a single cell in a plant, which is an incredible number. This is how they're depicted. They unwind and wind up, and they're really phenomenal, and tremendous amounts of study are being done on enzymes. And the next phase, I think, in farming and gardening is figuring out how to produce more enzymes in the soil food web, or using the soil food web, or more of the nutrients that the plant uses to make these enzymes. So you've got carbon, hydrogen, and oxygen, which is about 95% of all plants. The only reason why it's important is because this is what we make beer out of. And you get the minerals and the oxygen and the water from the root system, and you get the CO2 from the air. It goes through the stomatus. And these are the 14 mineral nutrients, and only 5% of the plant contains these mineral nutrients, which is not very much. And each one of them, of course, has an individual function, which we should all know, so that when you look at your plant and you see it's not doing well in one area or another, you can have some sort of a feeling for where to start to look for a correction. And each thing has a very important purpose. So if you don't have boron, you don't get the pollen tube, and you don't get the flower, et cetera, et cetera. You all know this stuff. Then there are all these wonderful charts that have pictures of what's wrong with your plants. Yeah, these are okay, but really don't rely on these. These are just starting points, because a yellow leaf that you might think is a result of a nitrogen deficiency can be caused by over 120 different combinations of mineral deficiencies. So it's not just nitrogen, or maybe it is just nitrogen, but it's a place to start anyway. So you can take those things and you can look this up, but the real way to figure these things out is to test. And this is something that most gardeners do not do. I hope all farmers do test, because information is knowledge and power. There's no way to know what's wrong with this cannabis plant just by looking at it. It could be a boron deficiency, it could be burning, it could be too close to to a light, but there's just simply no way of knowing. You have to sort of figure it out. Now, these 14 mineral nutrients, which make 5%, they're in the plant. And the amazing thing is, these nutrients at some point in time combine together, or the bonds form and create life. Whew. Now you got to really think about this. You take these 18 elements and you put them together the right way, and you create life. So you can go from these inanimate things that you buy in a bag and you throw down on your soil, and the next thing you know, you're getting life. It's sort of an amazing thing. I always like to tell people, 17 nutrients, I always like to tell people, that you may not be a vegetarian, but that piece of meat you ate definitely was. And it's always amazing to me that you take these 17 nutrients and you make everything that we eat with 17 nutrients, which is pretty incredible. And of course, they're delivered through the soil food web. And they are all converted by the soil food web, by the organisms in the soil food web, into charged particles. They don't go into the plant unless they're a charged particle. And what makes the charged particle? The soil food web critters. Who knew? I certainly had no idea. The only one that's an exception is boron. Sometimes boron can get into a plant without having a charge on it. All right, so how do the plants eat? Well, you have to learn a little botany. So we've got a little bit of chemistry, now we have to learn a little botany. This is a root, as you know, and there's the root tip, and my God, have we learned a lot about root tips over the past just couple of months. that change completely the things that we know. I'm going to go into it in a little bit more detail in my second talk, but there's something called rhizophagy, which was basically discovered years ago, but in the past month has become very, very prominent in soil science discussions, because rhizophagy are bacteria that enter a root. They go through the root tip, the meristem, those cells that are undifferentiated. Once they get into the plant, they take off their shell. So it's a bacteria with no shell around it. And then they go up against the inside of the cell wall, and oxygen is poured on them by the plant, steals the nutrients, and then after they've given up the nutrients, the bacteria move through the meristem and then come out by forming root hairs. It may be that root hairs are formed by bacteria, by the plant and the bacteria. Why? So that the plant can get those bacteria back out into a spot in the soil that the root has not already mined, or that a bacteria hasn't already mined and brought back in. So it goes out the root hair, puts the cell wall back on again, goes out and gets more nutrients, and then goes back in the plant. Now, we used to think fungi were the only things that did that. Rhizophagy, you're going to be hearing a lot about it, I'm sure. Other things that drip out of these are coming out of the meristem area. Again, we used to the slough, the tip. They used to talk about slough cells. These slough cells are what's known as xDNA, the same thing that's in your white blood cells. These are white blood cells. And they are produced by the plant. They go out into the soil, not to get food, but to tie up, to cleate things that the plant doesn't want taken in. So it ties it up in the soil so it can't go into the plant. It changes the charge on it. It clumps them together. Whoa! This is the same thing that happens in your body. Unbelievable. And that was only discovered a couple of years ago. So here's the pictures of the root hairs. And I used to talk about it. I say there could be more than 20,000 root hairs on an area equal to a fingernail, an average of 5 millimeters long. Surface area of these root hairs covers 3 square feet. And we used to talk about them just because they're out there mining soil. But they may actually simply be deliverers of bacteria. Holy crow. Unbelievable. Got to figure this out. And frankly, it was just a week ago that I read the article, or 2 weeks ago. So I have to figure out what's going on. Now, there are ways to get into the plant, 2 different ways to get into the plant. The first way is how do we call this? This one here. This is the symplastic. So you go in the root hair, and you get inside the cell, and the cells have a little hole between them. They got a lot of holes between them. And you can go from one cell to the next cell to the next cell. There happen to be 18 billion cells, or is it trillion? Doesn't make any difference. It's a number too big. And they're all connected. And so you can get in the cell, and then you can move throughout the entire plant, assuming you can get by this little barrier here, and you get in and you go into the plant. Or you can go into the root hair and get into the wall, right? All plant cells have a plant wall made out of cellulose. And it's sort of, it's like a mesh. And you can travel through those walls all the way through the plant without ever entering the cell. And what people don't realize is that we've got all sorts of bacteria and fungi living in these cell walls and doing all sorts of stuff for the plant, sometimes producing antibiotics, sometimes eating a bad guy, sometimes just sitting there taking up space. Unbelievable. And nobody really ever talks about it. Now, that wonderful water is brought up through this wonderful plumbing system that we know all plants have. And the xylem, of course, is the heart of the plant. And what happens is these nutrients that are produced by the soil food web and a charge is put on them, get into that water, which is a solvent, and the water brings it into the plant in an interesting fashion. So what happens is you have water going in the root, whether it's going through this in plastic, it's going into the cell, it goes into the xylem, goes all the way up, and it comes out the stomata. And you've got a column that's very much just sort of like a rope. And what happens is, because of this wonderful power of those hydrogen bonds, is that you get one molecule going in the root and one molecule coming out of the stomata. As a molecule comes out of the stomata, it pulls up this chain of water that's all connected by those wonderful hydrogen bonds, and it pulls it up one molecule at a time. Unbelievable. It's just like a rope, with one end in the soil, one end coming out of the stomata. You pull the end out of the stomata, and you pull water into the plant. Neat, very neat. And then, of course, you've got all of these wonderful little systems inside sieve tubes and plates, and but you've got these sinks where you've got sugars that go, and oh God, I'm walking around on my, where you've got sugars that sort of control the chemistry. So you get osmosis and diffusion, and it causes water to flow in one direction or another, trying to dilute the sugars. And so things move through the plant. All right, so then I had to learn a little bit of cellular biology in order to figure out, because I still don't know what's going on. I know how the water gets in the plant. I know the water can bring nutrients into the plant, but I don't know how they really get inside the plant yet. I know they have a charge, and so I had to take a look at this cellular biology stuff. And this is where, size really it makes a difference. So let's take a look at the size. If an atom was the size of a corn kernel, right, then a complex molecule would be the size of a squirrel, a simple molecule would be the size of a pepper, and a plant cell would be like one of these Sealand container ships with all the stuff. That's a single plant cell. And a tree has 18 trillion cells in it. Now remember, I said each cell had 42 million enzymes in it. So multiply 18 times 42 million, and you'll understand why enzymes are so important. And that's really kind of an amazing thing. So I can't remember why I have North America. Oh, if a tree was the tree would be the size of North America. That's what it is. Anyway, we're talking a tremendous number of cells. 50 plant cells at the period at the end of a sentence. All right, 5 to 50, but that's a lot of plant cells in there, and plants have tremendous numbers of cells. That's really, really, really small. I live in Alaska. I'm allowed to pick on her. So the other thing about it is that one plant cell has 100 to 200 trillion atoms in it. So we're talking about some pretty complex stuff. You people are farmers and you're out there working. You don't think about the minutia of the plant. Holy crow, 200 trillion atoms in each individual cell. 18 trillion cells in that apple tree. Wow, that's a tremendous amount of atoms. And we really know very little about them, don't we? I mean, it's sort of one of these things. We should know a hell of a lot more about them than we do. So hopefully you'll buy the book and learn a little bit about it. Because this is really mind-boggling stuff. I mean, it's crazy stuff. I'd put that in there just to make it even. All right, so proteins. Let's just talk about proteins. 10,000 different kinds of proteins in every individual cell of those 42 million. Holy crow. It's unbelievable numbers. Now, the other thing about cellular biology is that we tend to think of things in 2 dimensions. This is how I learned about cellular biology when I was in 10th grade. Take this home, fill it out. Okay, but things are 3-dimensional. They're not like this. They're 3-dimensional. And so, you got to be thinking about these 18 trillion cells in a 3-dimensional. Not just an abstract, flat fashion, because they are 3-dimensional and they're really incredible machines, and we just don't give them enough credit. They're tiny. Brian, but it's incredible. If you magnified, let's just go like this. So here's a cell with tremendous amounts of chloroplasts in it. It's got that cell wall around the whole thing. Each one of these cells is connected to other cells, and this is the cell wall that I just showed you there. The cell wall is porous. It's made out of cellulose. It's literally sprayed out of the cell, and it makes the cell wall. It's like cotton candy being made. It's really an unbelievable process, and every plant has a cell wall. So the stuff is spun, put into the cell wall. It's porous. All sorts of microorganisms can live in this cell wall, and it's an area that people never really think very much about. All right, so then, let's see here, if I can get this to work. You have next to the cell wall a layer called a plasmalemma. It's truly a plasma, like a fire, like your television screen. You know how you touch your television screen, you can move your finger around it and you can hear the static. It's a plasma. And it's a layer that's just inside the cell wall of every single plant. And it's a double membrane. And so what it's made out of are individual molecules that look like this. They have a head and tails. The head, let's see, the head, I always get this wrong, the hydrophilic and hydrophobic. So the inside, water is repelled. On the outside, it can kind of merge with water. All right? Now, this is around every single one of those 18 trillion plant cells. So the way to look at this membrane is, and this is what it looks like in a real picture, and there's another picture of it. But the way to look at it is sort of like a peanut butter sandwich. Okay? So you take a piece of bread, you got the water-loving bread side, and you put the hydrophobic peanut butter on the inside. And you put two of these pieces of bread together, and you've got your cell membrane, right? So water can get in the outside on both sides, but once it hits that middle, it can't get through it. So it doesn't really go through. And that's what happens. And so what does get through are oxygen, very small molecule is able to get through, and CO2, very small molecule able to get through. The other stuff, very long time to get through on its own. So we say they really don't get through. None of this stuff gets through. So how does it get into the plant? How the heck does the plant eat? Well, it turns out that this double membrane layer has all sorts of things stuck in it, embedded proteins. And these proteins act as tunnels that allow the food to go into the plant. This is what they look like in a picture. They're in rafts, and they float in that plasma that's right up against the cell wall. And each one of these little guys has different ways of letting stuff in. So there's 3 or 4 different ways. Some of them act in different ways. But these proteins do more than just let the food in. They let the plant communicate cell to cell to cell. Okay, so you get signals that go through these things, et cetera, et cetera. Only thing about this that you have to really appreciate is that only one kind of molecule can get through the tunnels. So there's a special set of tunnels for water. There's a special kind of tunnel for phosphorus. There's a special kind of tunnel for nitrogen. And the plant has to make these tunnels itself. And some of these tunnels, like the one for boron, are only used maybe for 7 or 8 molecules. But the plant has to take enzymes, take nutrients, and put them all together in order to make the tunnel. Insert it into the plasma membrane, and it has to work. And these are very complex machines. So, they act as revolving doors, some of them act literally as tunnels, some of them act as seesaws, some of them act as catapults, and some of them actually produce inside the plant hydrogen ions, put them outside, and those positive hydrogens attach to the negatives and some of the nutrients, and then bring them in through the tunnel, through active transport. And it's just an incredible, and if you're not the right kind of molecule, you don't get in. Simple as that. And so what some people have done is they figured out how to mimic these molecules. That's how Roundup gets in the plant. That's why each and every one of us here has Roundup in our bodies, even though none of us asked for the shit. Because it gets into the plants. It gets into the plants because those bastards figured it out. We can make it look like a phosphorus molecule. And that's what it looks like. And it sneaks through the phosphorus tunnel. Whoa, interesting. So it only goes through the kind of tunnels that you want. Let's see here. So you have active transport, you have passive transport, and this, of course, is the glyphosate molecule going through, which is a terrible thing. Special tunnel for water called aquaporins. They couldn't figure out how water was getting into these cells so quickly. And then they discovered these aquaporins, and they were the first tunnel that they discovered. And you have them too. In your cells. Your cells work very much like these, and you have aquaporins in your body. And water goes in one molecule at a time. Now, so you have this cell with a cell wall, and then you've got this membrane, and this membrane has all these tunnels. And that's how plants eat. They use these tunnels to get the food in. And then once you get into the plant, then you're in the cytoplasm of the plant. There's this big vacuole in the inside of the plant, just this air bubble, and that air bubble is what keeps the turgidity of the plant and the shape, et cetera, et cetera. And it is also a double membrane, and just like this one here, and it also has these tunnels in it, so that it can get rid of and take up poisons and all sorts of stuff, and keep the balance proper. If it turns out that you need to have less calcium in here in order to get calcium to go in, then it puts the calcium in here so that you can get the osmosis and diffusion to work. What an unbelievable factory when you think about it, and I hope you are. And there are 18 trillion of these operating constantly, 365 days a year, 24/7. Unbelievable. All right, let's see here. So that's how plants eat. They take their stuff in through charged particles through these tunnels that go through the cell wall into the plasma membrane, through the plasma membrane into the cytoplasm. Okay, you give it a little water, and it gets what it needs. And it's just that simple. And these are the pathways that you've got to be aware of in order to know what you're doing. So you have the apoplastic and the symplastic. And so next you have these little plasma holes that are in between the cells that connect each individual cell. So if you took a balloon, which is basically a cell, and you divide it, right, by just squeezing it, you're twisting it, right? Well, you end up twisting it. There's a connection between the two. It's just twisted, but there's a connection between the two cells. And that's what happens in cells. They divide, but there's always these little holes that connect each other. And so you get these little tubules between cells. And in order for molecules to go from one cell to another cell, they have to travel through these little teeny tunnels. This is what they look like. And they enable the entire subdivision of plant cells to be connected. You can go from one spot to any other spot in the plant by going through cells. You never have to go outside the cell wall. You never have to go, you just go right through the individual cell system, which is pretty amazing. All right, so then you've got this soup inside the plasmalemma, and in the soup cytoplasm, you have all of these little organelles that do all sorts of things, like you get the chloroplasts and mitochondria and all that kind of stuff, and they're in there, and these are the chloroplasts and the mitochondria, which we all now know are actually forms of life that somehow got engulfed inside a cell, and the cell and the forms of life decided, hey, this works. Let's just keep this little relationship going. So these guys have their own DNA, their own cell walls. They reproduce by themselves inside the plant. Wow, pretty amazing. And they both give the plant energy. The plant has a redundant system for energy. 2 different systems, not just one. And they got into the plant by something known as endosymbiosis. Again, where they got into the plant and the organism said, this works, let's just keep doing this. So they're able to make their own proteins and do all these things. And these guys, of course, are just unbelievable batteries. And they have all of these unbelievable plates that move depending on where the sun is as they move. Whew, man, complex. I mean, really, really, really complex. But independent organisms that make plants work. And let's see here. Yeah, don't need anything on that one. There they are. They're in there doing their thing. You can have 60 to 100 of them in a plant. There's the mitochondria. These are definitely like little batteries. They produce energy like crazy. You can have 50 to 60 of them in a cell, depending on what the function of the cell is. You have more or fewer of them. And again, they're only partially dedicated, not dedicated, but owing to the plant for reproduction. Most of the reproduction they do on their own, which is really an incredible thing. Let's see here, what else we got inside the plant here? We got the nucleus, of course, which is where the DNA is, and it's protected from the rest of the plant. It has its own envelope around it. That envelope has little holes in it. Certain molecules can fit out that hole. Very few things can go in. And this, of course, is where the DNA is. And it is connected to the endoplasmic reticulum, the rough and the smooth, okay? And on the rough, you have all these things called ribosomes. And ribosomes take replicated DNA and duplicate it. And they're all over the place. This is actually a picture of a strand of DNA between 2 nanocarbon things. You can almost see the little DNA things in there. Unbelievable. About 1.5 years old. So it's kind of cool that we can now see DNA. And then you have this rough endoplasmic reticulum, and the endoplasmic reticulum takes the DNA after it's made and starts to package it up. It can also take bad stuff that the plant really wants to get rid of and envelope it into little packages. And then it moves it on to the smooth endoplasmic reticulum, and it also continues to break down the toxins and continues to package the good stuff that the DNA has made. Now, the ribosome is just like one of those little knitting machines that kids use, where you just kind of make these little things that come out at the end. This is exactly the same way that a ribosome works. The stuff goes in and it comes out the end, and it's just like, oh, how did that happen? So all sorts of amino acids sequences are duplicated by the ribosome. Really kind of a neat thing. This is a picture of a membrane protein. This is the membrane protein being produced by a ribosome. Took this picture, by the way, between the second and third buildings in the Chicago airport. Anyway, this is the googly apparatus. Googly is the only thing in the body that's named, or in a plant cell that's named after a person, and it's like an upscale gift shop. So all of these molecules that are made in the ribosome and packaged and started in the package and stuff in the endoplasmic reticulum finally ends up in the googly apparatus. The ribbon is put on it, the paper's put around it, a label's put on it, and it's shipped out. And some of it's shipped out to the cell, and some of it's shipped out to the membrane to go into another cell. Beautiful process, and just sitting in there, and we have no idea. So this is what the whole complex looks like put together. And they're all connected in this beautiful little pathway. Unbelievable, another depiction of it. The googly finishes the proteins. Let's see what else. It moves the stuff out of the cells. Packages it up. It's beautiful stuff. And then you might hear some sizzling and gurgling if you're walking around inside a cell, because there are all these little things that contain unbelievable acids. And they take the bad stuff and they break it up. Some of the bad stuff is broken up and then it's reused. Some of it's broken up and just held because it's so toxic that it's no good. But That's what happens. So you have all these little lysomes in there running around doing stuff. And then you've got that thing full of, in the middle, that tonoplast. It sort of holds the pressure of the plant together. It can be very, very large. It can take up to about 80 or 90% of the cell, and it's incredibly important. And then you've got all of this structural stuff inside the cell. All of these scaffoldings and wires and things where communication takes place and where molecules move along tracks. Unbelievable stuff in there, a cytoskeleton that we never think about. But each one of those 18 trillion cells has this stuff in it. You've got this unbelievable, you have tubules and tunnels and literally tracks. And there are pictures of molecules literally walking along these tracks with little arms. It's unbelievable stuff that goes on, and a lot of these things are woven together in ways, in patterns, so that they can increase the amount that they can have up to 5 times in a space, because it goes in different shapes, and it's not just a straight line. So you have microtubules, and you have actin fibers, and all of this stuff is communicating inside the cell, from cell to cell, from plant to plant. Beautiful stuff. And this is what it would look like with all this stuff. And this is the infrastructure that we don't think about very often. Different depictions of it. And then you put all this stuff together, and you've got a situation where a plant, like one of these giant Atlantic pumpkins, can put on 40 to 70 pounds a night. 40 to 70 pounds a night. Wow. Why? Because it's got 18 trillion little factories in there running around like crazy, doing all this wonderful stuff. All right, so this is all kind of an amazing, let me just read this part, because if you have the cell the size of a football stadium, 300 million times bigger than a regular cell. Cellulose, right, the stuff on the cell wall would look like wires with peanut-sized electrons. You'd have the plasma lemma would be about the thickness of teeming with microbes. You've got peanut electrons all over the place, literally the size of peanuts. It's noisy as hell, sparks everywhere, 50-foot mitochondria. Let's see, you would have actin and bridges, and you wouldn't be able to walk around. The thing would it'd be impossible. 300 times the size of a cell, all this stuff going on. It's sort of, you put all these pieces together, and it sort of looks like this. Let me see if I can get this to work. Does not always do it. No, there it goes. All right, so this is a cell. There's the plasma lemma. There's one of those tunnels. This is a little molecule going through there. Oh, it's moving down these tubules. These are all of those actin fibers. Look at the stuff. Oh my God, here's one of these little engines that's producing hydrogens, that's putting outside the thing. I'm peeing in my pants. I love this stuff. Look at this stuff. God, all this stuff going on in the cell all the time. What it's trying to show is how mitochondria work. So you got to get these electrons going. You got to get the electrons in the right place. Enzymes everywhere, blah, blah, blah. This is Harvard University does this. Every year they have a thing, and it's got music to it and everything else, which we're not playing now, but it's really kind of incredible. This is inside a single cell. That was a ribosome. Look how this thing travels. This is how, and it happens inside plant cells like crazy. You have no idea. You've never seen this stuff before. Unbelievable. There's one of these things popping out of nowhere. All right, anyway. It's unbelievable stuff. All right, so we're not done yet. Because we had to learn a little bit more about botany. This is the meristem. You've got the 3 different systems inside so you're either assigned to be a leaf or a stem or something. And so this is a broccoli plant forming, starting up there with nothing and moving down, becoming a broccoli. You snip off the tip of your plant, your cannabis plant, for example, and you get 2 new ones because you change the way the hormones run in the plant. Mycorrhizal fungi. The reason why you get those big pumpkins is because of mycorrhizal fungi. Look at this mycorrhizal fungi in this cannabis plant. Biggest leaf I ever grew in my life. Turned out to be a male plant, unfortunately. But it's okay. That's okay. So it's the microbes that convert everything into food that's usable by the plant. That's how they eat. But let me go through the other stuff. This is how they take the stuff in. Blah, 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 and blah, blah, blah. So now let's get to the other part. So Horton Hears a Who. What the heck was I talking about this stuff for? So, you know, I'm doing this stuff. I write this book, and all of a sudden I start, whew, man, my mind starts to do some weird things, you know. And I start thinking about Horton Hears a Who. You know, we all know the story. Horton hears the Who, you know, and oh, help me, help me. You know, so blah, blah, blah. And, you know, I submit that we're all living in this Horton Hears a Who world. So you take a look at the cell wall. What the heck is the difference between this cell wall and these bricks? They look alike. They do the same thing. They're made the same way. How about this clock and this cell? They look exactly alike. They work the same way. They're complex, all sorts of crazy stuff going on in there. How about this? So we have a double membrane, right? Muskox, the Apple building. It's a double membrane. It's what it is. Works just the same way the double membrane works in a plant. How about this? Let's see here. So we've got all of this membrane around a roof. Same thing as the membrane. And wait a minute, protein pumps and stuff. Revolving door. Wait a second. It all works the same. You go through a revolving door, you're just a molecule going into a new cell. It's amazing. You know, it works the same way. These ribosome things, you know, what's the difference between that and a factory where things are made using a template? Whew, it's very similar, you know. Which one of these things is the plant root? Which one of these is the baked CD? They look awful alike. A plant cell. A soccer ball. Wow, you know, I began to think craziness, you know, and then I think about what happens in the googly body. No different than what happens at the FedEx store. Stuff gets packaged and shipped on. It's exactly the same thing, you know. And how about this stuff? It's just like, you know, fish going back to the same river. They only go back to that one river. The salmon. They don't go back to any other river. They only go back to that one river, just like the molecule only goes through that one molecule. Subdivision, plant leaf. You're able to drive on the roads. You're able to go through the, amazing. You know, transportation and communication structure. What's the difference between inside the cell and this little wooden toy system? They're very similar. You know, which one of these is the cell? Which one of these is the broccoli? Look at this. This is the actin fibers. This is the port of Muskie. That's exactly the same. Unbelievable. Okay, and then I was walking around with my wife. I'm going to be about 6 minutes, not 5. Walking around with my wife, I see these, wait, I got to get a picture. She goes, what are you taking a picture of that for? I said, what are you talking about? Those are enzymes. You know, and then she says, wait a minute, stop this. Solar cells. Exactly the same. Holy crow. Storage organelles. Holy crow, exactly the same. Unbelievable. Now, listen. Mitochondria and Cheetos. Come on. Come on. I mean, you know, this really drives me crazy. I'm going nuts. Just a coincidence? I don't think so. One of these is a starfish. Crazy. Hey, plasma lemma between two cells? What's the difference? You know, it's the same kind of thing. Just to make it a little bit more fun. Holy crow, like, you know, look at this. This is a national monument. I took these pictures in the Salt Lake City airport. Wait a minute. It's just like those floating little tunnels. Oh my gosh, what's going on here? Here's the sun, here's the plant nucleus. Oh my gosh. You know, here's the northern lights. It's nothing more than a plasmalemma. It's just like, holy crow, what do we got going on around here? This guy is spraying a wall, and it's exactly the same way that the cell's wall is made. Okay, this is a picture of a coastline, and this is a plasmalemma. Very weird. And what is the difference between this and actin fibers? This is the United States and Europe's internet traffic. And this, come on, This is just too crazy, you know. So here's my point. Here's my point, and my second talk is much more serious. Important here's a who. You know, well, it just gets too overwhelming. When I sat down and finished this book, and I looked at the cell, and then I looked at a picture of the universe, and I could not tell the difference between the two of them, I began to hear the who's. And so I say this to you. When you go out there and work on your farm or in your garden, you know, pay attention to the little things that are happening in those 18 trillion cells in every one of your plants. But every now and then, you need to just scream out loud, kill Donald Trump or something like that. Scream out loud, okay, so that they hear you. Because we live in a Horton Hears a Who world. Simple as that. I thank you very much. You are a terrific audience. I don't think we need questions on this one, but at 2:45 it's going to be much more information, much less entertainment. Thank you very, very much, folks. Oh, by the way, if you'd like to buy copies of the books, they have them in the other room, and they don't want to carry them back, so buy them from them. Doesn't help me, but it will help them very much. And one last thing, how about a round of applause for the terrific people who put this thing together?